Okay, let's begin. So in the last class we looked at basics of sampling and we started to look at quantization. So we'll continue from that. And the basic flow we'll take in this course is this. First we'll try to understand ADCs at a system level. So that's why we started to look at basically the two basic operations, sampling and quantization. And then we'll try to understand how we can characterize or measure the performance of an ADC. Because once that is done, if you take any ADC data sheet, you will understand what each thing is. Okay, that will be the focus in the first few classes at least, and then we'll go to the circuit design aspects. Okay, and as we saw in the last class, quantization, we can have two kinds of characteristics based on where the middle of the full scale range is lying. So it could be either at this jump or in this flat region. And now I'll consider this mid-rise quantizer as an example and proceed, but the same can be done with the other kind also. So say I consider a 2-bit quantizer. How many levels I'll have? 4 levels. And let us say my full scale range is from minus Vref to plus Vref voltage. Then what is my step size delta? I mean range of minus Vref to plus Vref divided into 4, 2 Vref by 4. And in general, if you have n bits, what is the step size? By 2 power n. That's all. Okay. Great. So let me quickly sketch the characteristics once. So this is the input y, output v. So the minimum, maximum and minimum. So split into 4 levels, like 4 regions like this. So I'll normalize with respect to the step size. So this is 1 delta, 2 delta, minus 1, minus 2. So again, this region of 0 to 1, I'll quantize it to 0.5. So here it will be 0.5 delta. So again, I'll normalize everything with respect to step size so that it becomes easier. So this is plus half, minus half, and then I'll have something like this. Okay. Great. And in the last class, we already established the fact that the quantization is a linear operation or a non-linear operation. It's a non-linear operation, so it's not straightforward to actually sit and analyze. But of course, if you want, you can do it, but that is not our goal. Our goal is to just quickly understand it and make circuits that do this job, right? So for our purpose, we'll simplify this operation and reduce it down to this. So we know that we have the input y, and the output v is obviously not same as the input y. So how can I model this? I mean, v is not same as y. So what is the simplest model I can? I mean, you can think of it as adding some other signal q, that when adds with the input y, I get some signal v. Simplistic model, right? And this q is called the quantization error. That's basically the error that you make when you round off the input. And if you know both the input and output, how can I find the quantization error? V minus y. So it's basically the quantized version of y minus the y. Okay. So let's quickly plot and see how this is going to look like. So I'll sketch the quantization error here. So again, this is q, this is y by delta. And this is already the quantized version of the input. So I'll also draw a straight line so that this portion is there. Draw a straight line like this. Okay, so this is basically y, or I mean everything is normalized, so it's basically y by delta and stuff. Okay, I'm not being very strict in this. So okay, if I subtract these two, what do I get? At 0, what do I get? I mean 0, how can it be 0? At 0, the straight line is 0, but the other guy has a jump. So we'll have a jump. And what will be the jump? What will be the minimum and maximum value? I mean, is it fine? I mean, at 0, it jumps to either plus half or minus half, right? So I'm basically taking the difference between the step curve, which is the one in blue, and the green curve. So this will be what? So it will also jump like this, right? And if I go to the positive side, what will happen? It will try to drop to 0, right? And again at this point, what will happen? It will jump again. I mean, wherever you have the jump in the step characteristics, even in the quantization error plot, you will have the same jump, and then it will do this. And wherever these two guys intersect, it will go to 0. So same thing will happen here. So here at this point you will have a jump, and then you will have something like this. And you'll find that as long as the input is within this full scale range, the quantization error will also be within plus half and minus half. Basically, this is also normalized with delta. Okay. And if you exceed beyond this, the quantization error will also keep growing like this. Okay. So of course here we can see one thing clearly. As long as my input is within the full scale range, what is the limit of the quantization error range? Minus delta by 2 to plus delta by 2, right? So this guy will be in minus delta by 2 to plus delta by 2 if my input is within the full scale range. Okay. And if the input is not in the full scale range, the quantization error also grows beyond bounds, because here you have hard limited the output but the input keeps growing, right? And this condition is often called overloading. Okay. Great. So now we have got just one information about the quantization error, that is, as long as the input is within bounds, the error is also within plus or minus half delta. But that is not good enough to do any analysis. So what we do, we decide to make some assumptions about this quantization error, and these assumptions might actually not make any sense at all, but it turns out these assumptions work well in real life, so you don't worry about it. So the first assumption is, see here, do you think this quantization error is dependent on the input or not dependent on the input? It's strongly dependent on the input. That sort of makes it difficult for us to analyze it, right? So if you are in the process of making assumptions, you want to make assumptions that will make your life simple. So what is the assumption you can make? So it's basically independent of the input. So which means I can treat it as independent signal. I can consider it as some random signal. And for this reason, it's also referred to as the quantization noise. So now that you have declared this guy as a random signal, to how do you treat random signals? How do you analyze them? Yeah, you need statistical measures. So you need to define the probability density function. And again, we are in the process of simplifying things. So what is the simplest PDF you know? I mean, Gaussian has like complicated shapes, right? I mean, as you pointed out, the simplest thing is uniform. You'll assume that it has uniform PDF.
What is uniform PDF?
Quantization error. So if I plot it, this is Q. This is the probability, say PQ of Q. I know the minimum and maximum ranges, right? What is that for Q? Minus delta by 2 and plus delta by 2. So it's going to be flat. And what is the value here? The area of this curve should be 1. So this is going to be 1 by delta. Okay, so So let's actually see if this assumption is indeed valid. So for that I did some exercise. So I did an experiment wherein I generated a signal which is a ramp going from your minus Vref to plus Vref, sampled it and then quantized it, and then I found the quantization error and then plot the histogram. So this is what I get. So here I have quantized with 6 bits and you see that the distribution is almost uniform, right? And I repeated with 10 bits, it's even better. But of course, we don't deal with RAM signals, so
What was in the y-axis?
y-axis is the number of bins. These are the values of the quantization error normalized, and these are the, I told, yeah. It's basically, you can, this by the sample size will be the probability, right? Okay.
And
The number of sample size.
so what is the y-axis?
See, this is basically a proxy for the PDF. This is a proxy for the probability density function, right? This is not normalized. If you normalize it with respect to the sample set, you get the probability. So yeah, but of course we don't deal with ramp signals. So I took sinusoids because any signal you can decompose as sinusoids. So let's say I take a sinusoid, say with a frequency of 201 hertz. So I sample it at say 1000 hertz. Again I quantize it. Okay, and then let's say I take 1000 samples of this. So the sample size is 1000 here. And then I do the same thing, find the quantization error and then plot its histogram. So this is what I get for a 6-bit case. Again, it's not exactly uniform, but more or less it appears to be uniform, right? So a few change.
Before it was more uniform.
Yeah, that was basically because it was ramp. This is a sinusoid, right? So when I did it with basically 10 bits, it's looking like this, but the point I'm making is it is not exactly uniform, but if you look at it from a far off distance, it does look like a uniform distribution. It works reasonably well, that's all, right? So by this we'll be tempted to conclude that, this we can approximate the distribution to be uniform. But before jumping to any conclusion, let's look at another example. So in this previous case, I took what was the sinusoid frequency? I took 201, right? So I'll change it to 200 hertz now. No big change. The other thing is same, so I'm going to sample at 1000 hertz. Going to quantize it. I'll basically collect 1000 samples of this guy.
Equidistant.
Sorry? Yeah, when I'm sampling it, it's all equidistant, right? That's all. So I take 1000 samples and then do the same experiment. And voila, I get this. So basically, I don't see it to be uniformly distributed. It seems to be taking only, few values. And even if I go for a 10-bit, it doesn't change so much. So what do you think is happening?
It's a multiple, frequency is a multiple of sampling frequency.
So, okay, let's write the signal. So in the first case where it worked, it was 201 times t. In the second case where this approximation was not looking valid was when the frequency was 200 hertz. Both of them were sampled at 1000 hertz. Yeah, so why? Yeah, it is a multiple of 200 is a multiple of 1000, so why is it partial to multiples? Yeah, so if we look at the discrete time sequence, right? So what is the discrete time sequence here? 2 pi into 201 by 1000 times n. Is that clear? So what is the sequence I'll get here? It's 200 by 1000 and 200 by 1000 is 15. So it's basically n by 5. Okay. So what is the period of the sequence? I mean, this is a periodic signal, right? So what is the periodicity of this? 1000 samples. After every 1000 samples, it's going to repeat. Okay. So here the periodicity is 1000 samples. And what is the period here? 5. Okay. And remember, in both these cases, I took 1000 samples and then quantized it and then did it. Okay. So in the first case, when I took 1000 samples, all 1000 samples were all distinct, right? Because the periodicity is 1000. If I take any 1000 samples continuously, it's going to be all distinct. Whereas here, although the sample set is 1000, I have only how many distinct amplitudes? Only 5 distinct amplitudes I have. Okay. So if this is the quantizer characteristics, in the first case I was exercising all possible, the entire region of this curve. Whereas in the second case, where I had only 5 input amplitudes, I was probably exercising 2 or 3 of them. Okay. And that's why it was not uniform. So the bottom line is, as long as you have busy signals wherein you span the entire range of the quantizer and make sure that there is sufficient variation in the signal amplitudes from sample to sample, the assumption that the quantization errors probability density function is uniform is valid quite well. Okay. And that's what will happen in real life. The real life signals we encounter, they'll all be BC signals. So this works quite good. So now that we know its PDF, let's make some more calculations on its statistical quantities. So this point is clear. In the first case, when we took 1000 samples, all 1000 samples were all distinct, right? So the input was spanning the entire range. So which means we are exercising all possible levels in the quantizer. In the second case, where I had only 5 distinct amplitudes, I most likely were exercising only 2 or 3 of the quantizer characteristics. That is why the quantization error was also, falling in 2 or 3 bins. It's not uniform. So for this assumption to be valid, we need to have what are called BC signals, which means the input must span the entire range and there should be sufficient variation from sample to sample. Here it is not the case in this guy. Okay. Is that okay? So let's move on. So let me draw the PDF once again. So it's spanning from minus delta by 2 to plus delta by 2. This 1 by delta. So what is the mean of this guy? Mean is 0 because it takes both positive and negative values with equal probability. What is the mean square value? Mean square value is the power, right? So what is the power? How can I find? Expected value of q square. How will I compute this? Yeah, but how do you compute it from? How do you find d of x?
Of q square after minus delta by 2.
Yeah. Q square into?
1 by delta.
Q square into the probability density function, which is 1 by delta dq, and you work it out, you will get this to be delta square by 12. Just simple integral. I'm sure you would have seen this result somewhere or the other, so I'm just writing it. And what is delta here? If I have an n-bit quantizer, what is delta?
2 by 2 by
2vref, which is the full scale range, by the total number of levels, which is 2 power n for an n-bit quantizer. Okay. And remember, this is the power of this quantization error, right? And if you want to have a good ADC, you want this error to be small, power to be smaller or larger. You want this to be as small as possible. So this is one metric in which you can compare the performance of an ADC to see how smaller this quantization noise error is.
the more the number of bits, the lesser the.
Yes, right. I mean, here you can clearly see if I increase the number of bits, this delta will reduce. That will in turn reduce this power of this quantization error. Okay. But of course, just having a smaller quantization noise error is alone not enough. You also need to have a large signal power, right? Finally, what that matters is the ratio of signal to noise power, right? So in our case, we have a range from minus Vref to plus Vref. So what is the maximum sinusoidal signal amplitude I can apply? If I have to apply a sinusoidal, what is the maximum amplitude I can apply? It's Vref, something like this, centered around 0 with an amplitude of Vref. That's the maximum amplitude I can apply. So what is the maximum signal power I can have? Vref square by 2. That's the maximum signal power. So now I can take the ratio of these two guys, signal power and noise power, and get what is called the signal to quantization noise ratio. So signal power is Vref square by 2. So noise power is delta square by 12, and delta is basically this guy. Okay. So if you simplify this, you'll get what 3 halves to 2 power 2n. I mean, just work it out. And if you express it in dB, which is how signal to noise ratio is usually expressed, you take 10 log of this quantity, so you'll have 6.02 n. So much dB. Okay. So it's roughly 6n plus 1.76 dB. Great. So what that means is, and remember, this is the maximum SQNR you can obtain for sinusoidal inputs. So what this means is, if you have an ADC, say a 10-bit ADC, for sinusoidal inputs, the maximum SQNR I can get, how much is it? How much? Around 62 dB. Okay. Okay, so let me take it. So I have SQNR, this is roughly 6n plus 1.76. So if I find the number of bits from this, so many bits. Okay. And usually this is how we compute the effective bits, and this is often called the effective number of bits, or ENOB. Okay. I mean, we need to have this measure because, I mean, for all that matters, I can take a 4-bit ADC, add some 3 random digital bits, connect it to ones or zeros randomly, and put it in a box, and say I have 7 digital outputs, it's a 7-bit ADC, and sell it to you, right? But that's not the case. Just because I have some n digital bits coming out of my ADC, it doesn't mean it can effectively quantize to that much of resolution, right? And I mean, this is a very convolved case, but in a more practical sense, you'll have other non-idealities that might limit the maximum SQNR. Ideally, let's say for a 10-bit, we expect 62 dB, but because of a lot of other design issues, which we'll see later, you might not be able to hit that maximum limit. Although you have 10 digital bits coming out of it, your SQNR might be smaller. So that's why we need to characterize the effective number of bits that the ADC can resolve to, and this is how we define it. Okay. So the deal is, first you measure the maximum sinusoidal SQNR you can measure. Again, this is all with sinusoidal inputs. Okay. So you need to measure the maximum sinusoidal SQNR you can measure and then back calculate. So I give a sinusoidal input, I get some quantized sinusoid like this. Yeah. Yeah. We have considered it as a random noise. It's an additive process, so it's not. We have made it the linear block. Okay, so let's say I'm trying to measure this E knob. So I'm applying a maximum sinusoidal signal. So if I measure the output, I'll get a quantized sinusoid like this, right? So from this time domain signal, I'll have to find SQNR, that is, I have to separate the signal from the noise. But from this time domain information, it is impossible to separate what is signal and what is noise, right? So how do we differentiate them? I mean, is the question clear? We have to measure this SQNR so that we can calculate this effective number of bits. And for measuring the signal to noise ratio, I am applying a sinusoidal input. The output is looking something like this. From here, I have to separate what is the signal power, what is the noise power, and take the ratio. But from time domain, it is impossible to separate them out. So what can you do? I mean, okay, in time domain you can't do, right? So what is the next solution? If time domain fails, go to frequency domain. If your mom doesn't give pocket money, you ask your dad, right? That's all. So we'll do this in frequency domain. So next what we'll do is we'll take a quick detour and refresh our basics of spectral estimation. Again, we'll be dealing with both deterministic signals like the sinusoids and random signals. So we'll look at for both of them. First, we'll start with deterministic guys. So again, you know, if you have a deterministic signal, which means at any time, you know what the amplitude is, and you can take the Fourier transform. And how do I compute this? Integral 2 pi f d dt. Okay, and let's say this is a okay. I mean, you assume that signal starts from 0, right? This starting point is all up to you. So let's say my signal x of t is a voltage signal. So what is the units of Fourier transform? Again, this is dimensionless. dt is second, so it's basically volts per hertz. Fine. So basically, the Fourier transform, when you take it, is spectral density. So you can think of it as voltage or amplitude spectral density function, very similar to your probability density function, right? So what that means is, if I take the Fourier transform and say that at some frequency f0, the value is a0, it doesn't mean that my signal has a sinusoid at that frequency f0 with the strength a0. All that means is, if I take, say, 1 Hertz bandwidth around f0, say this is 1 Hertz. Around this 1 Hertz bandwidth, we have a whole continuum of frequencies, and the combined strength of all those frequencies is a0, right? So it just gives the measure in volts per Hertz. In a 1 Hertz bandwidth, what is the combined strength? So only if you have an impulse in your Fourier transform like this. So now at an f1, let's say you have a1, then you can say that I have a sinusoid at a frequency f1 with a strength a1. Okay. So this is in continuous time. Similarly, in discrete time, I can compute the discrete time Fourier transform. So again, I'll just write it. It is x of n j omega. Okay. So this is with simplistic deterministic signal. So let's then consider more interesting random signals. Again, random signals, by the virtue, we can't treat them as deterministic signals. We have to look at probability and statistics. So we look at statistical measures like mean and mean square. Now mean is basically the average of the signal. And what does mean square signify? It's the power in the signal. Again, without going into a lot of details, we'll be dealing with stationary signals. That just simply means that the statistical properties do not change with time, right? And for those stationary signals, we will consider, along with average and power, there is one other quantity that doesn't change with time, which is autocorrelation. Have you guys heard of this term before, all of you? Okay. Okay, so let's go through it quickly. So the definition is this. So you integrate x of t with x of t plus tau. It's t plus tau. T minus tau, it's convolution. So let's say you observe the signal for a time period t. So that is this t. You multiply x of t with a shifted version of itself and take the inner product. In English, it simply says how much the signal is related to itself at a different time instant, right? So basically, if I know the information about the signal at a time instant t, can I make any comment on the signal value at another time instant, say t plus tau? That's all this says. And at what value of tau do you think this autocorrelation will be maximum? 0. 0 means there is no shift. The signal will be maximum related to itself, right? So if I find Rxx of 0, what do I get? So what is this? X square of t dt. So this is t. This is basically the power. Okay. So now let's say at some value tau naught, I find that the autocorrelation is closely equal to the maximum value, which is the signal power. It just means that if I know the signal value at a time tx, with a very high confidence, I can say that the value at tx plus tau naught is also same. No, it's not periodic with t naught. It just means that the values are very similar. Higher the value of autocorrelation, with the high confidence level, you can say the value of the signal. Now it's all probability, right? What is the confidence level with which you can comment about the value of the signal? That's all. So this is in continuous time. So similarly in discrete time, you have all these, and you can define autocorrelation. So here it is all in terms of the number of samples. So you'll have 1 by n summation n, so of n plus m, and ideally you have to tend this guy to infinity. And similarly, if I compute the autocorrelation at 0, that will be the power of the discrete time signal. It's just same. So this is the time domain statistical measures. So similarly, we'll have statistical measures in frequency domain also. And for deterministic signals, we can look at the Fourier transform or magnitude of the Fourier transform. But for random signals, the amplitude doesn't make sense, right? We are interested in average and power. And for most of the random signals, the average will be 0. So instead of defining Fourier transform, which is an amplitude spectral density, what should be defined properly for this? We are interested in power, so it makes sense to define power spectral density. So here in frequency domain, we have power spectral density, or PSD. Again, Fourier transform, if I take the magnitude, it has units of volts per hertz. We want power spectral density, and what is its units? Volt square per hertz. So how can I define a power spectral density? If I take the magnitude squared of Fourier transform, what is the units I'll have? Volt square per hertz square. So what should I do to get volt square per hertz? I have to divide by time. And this time is basically the time for which you have observed the signal. And ideally, for all, like all statistical measures, you tend to infinite. Just a second. So this is the definition of power spectral density, right? Sorry. Again, just like your Fourier transform, it is a density function. So unless you have impulses in the spectrum, you cannot say that the signal has sinusoids at frequencies. Okay. So again, the physical intuition to understand this is, say you take a signal x of t, pass it through an ideal bandpass filter, say with a center frequency f0 and a bandwidth of 1 Hz. and then you take the power of the output signal, that will give the power spectral density at what frequency? F naught. It's again the power around a particular frequency in a 1 Hertz bandwidth. Okay. So other thing you should remember is this power spectral density is an even function. So if I plot it with frequency, it will be an even function like this. So you can either have a two-sided PSD wherein you show both positive and negative frequencies, or you can add up the negative frequency content to the positive side. So then you will have, let's say, something like this, only for positive frequencies. This is one-sided PSD. Okay. And we know that by definition, power spectral density at a frequency f is the power around f in a 1 Hertz bandwidth. Now if I want to find the total power in the signal, I'll have to look at the power contained in all frequencies. So how do I find it? Yeah, I mean, this power spectral density gives information around one frequency, but now I want the power contained in all frequencies. So basically I'll integrate the power spectral density, say from 0 to infinity. Again, here I have assumed that this is a one-sided PSD because I am integrating only from 0 to infinity. Okay. Now, from our earlier discussion, remember that power is also the autocorrelation at 0, right? So this is also equal to Rxx of 0. So what do you think is the relation between autocorrelation and power spectral density? It's a Fourier transform. So if I take this guy and take the Fourier transform, I'll get the power spectral density, right? So again, we can have the same thing in the discrete time also. So here I'll just quickly write for the sake of completeness. Here it is all with respect to n, magnitude squared of the discrete time Fourier transform to infinity. So this will again be two-sided or one-sided, but because of the fact that we are looking at discrete time frequency omega, we have periodicity in 2 pi. Okay. So for a two-sided PSD, we will have the span from minus pi to pi, unlike in continuous time case where it's from minus infinity to plus infinity. Similarly, for one-sided, we will have from 0 to pi. That's the only difference. And again, this hold good, this property again holds good if I take the autocorrelation function and take the Fourier transform, I get the discrete time power spectral density. Okay, and of course, if I know the, so similarly, if I were to find the power, how do I find? From the power spectral density, how will I find the power? No, it's still omega, it's discrete time frequency, so omega is still continuous variable, right? Integral, let's say one-sided PSD is xx of e power j omega d omega, but here you will have a scaling factor of 1 by 2 pi. Because you are dealing with this radiant frequency omega, you normalize it to 2 pi always. That's the only difference. Great. So now if let's say some signal has a power spectral density which is basically flat from 0 to infinity. So what will be the autocorrelation function? It's going to be an impulse, right? And signals with this kind of power spectral density, they are called white random process or white noise. Okay. And similarly in discrete time, you will have white noise sequence which has one-sided power spectral density which is flat from 0 to pi. Okay. Great. So the bottom line is If you have to find the path spectral density, I'll write only for discrete time here. You take the magnitude squared of Fourier transform, scale it by n, and ideally tend n to infinity. Of course, in practice, you can't tend n to infinity, so you collect large number of samples as possible, and then simply do this. Okay, but doing this alone might not be enough, because let's say I take a white noise sequence. Ideally, its path spectral density must be flat like this. But let's say you do, if you compute the path spectral density like this, you'll find a lot of variation around this value. Okay. And to reduce this variance, what you should do is this. So let us say you have decided to capture n points. Instead, you capture, let's say, more points. Let us say 10n. And you divide it into, let us say, 10 segments, each with n samples. Find the magnitude squared Fourier transform for each of these segments. So we'll have 10 such magnitude squared Fourier transform and average them out. That will reduce the variation in this. Okay. So in practice, how we measure path spectral density or estimate it is we compute the magnitude squared of Fourier transform but average them out. So I'll write it as expected value of this. So this is a more practical definition of a path spectral density. Okay. So again, I can show an example. So I've generated a white noise sequence, and when I directly took the path spectral density without averaging, I get this yellow curve. You see a lot of variation. Right, and the moment I averaged it, I think 4 times or something, I see the blue curve, the variation reduced, and then what? This is in dB, this is in decibel. And when I average it for 10 times, you see that it's more or less constant like this. Okay. And in practice, to get more averaging, what you can do is this. So let's say the same thing you capture for 10n. So the first segment you take from 0 to n like this. Now the second segment, instead of starting from here, you start with some overlap like this. Then the third segment will be overlapping like this. So this way you will have more segments for averaging, right? So if you don't have any overlap, if you capture 10n samples, you will have option for averaging 10 times, but with this overlap you will get more segments for averaging, and your estimate will be much better. And this is the Welch estimate of PSD. Okay. Now we have assumed some things about our quantization noise, right? So one is the fact that it is a random signal. Second, it has uniform PDF. And now that we have declared this guy to be a random signal, we'll have to make some assumptions about its path spectral density also. So what is the path spectral density do you think we'll assume? White, because that's more simple, so we'll assume that it has a white path spectral density. Okay. So we'll assume that it has a white PSD. And again, all these assumptions actually hold good in practice as long as you have those BC signals. Right? And remember that what is the quantization noise power? In delta square by 12. And how can I compute it from the path spectral density? Yeah, in discrete time I'll have 1 by 2 pi and then integrate it from. Okay. Great. So now if I apply a sinusoidal input, I'll get a quantized sinusoid at the output. So now what I'll have to do is to take the part spectral density of the output, SPV of e power j omega. I'll take a single sided part spectral density going from 0 to pi. So how will the part spectral density look like? I have both signal and noise. How will the signal appear in the part spectral density? You'll have an impulse corresponding to the sinusoid, right? And we'll also have quantization noise, which we have assumed as a white part spectral density, so it will look something like this, right? So if you look at the strength of this impulse, so that will give me the power of the signal, right? And to find the quantization noise power, you can actually take the overall power of the signal that comprises of both signal and noise, and then you subtract the signal power. That gives the noise power, and then you can take the ratio. Sorry? And again, to mind you, we compute this part spectral density as magnitude squared of discrete time Fourier transform. You take expected value of it, that is, we averaged it multiple times and divide it by n. Okay. So this is nice, but one issue is the fact that we have to compute the discrete time Fourier transform. And the practical difficulty with this is the following. So if I were to find the discrete time Fourier transform, how will I find it? How will I compute the discrete time Fourier transform? Summation 0 to infinity. Fine. Now there are two things. One is the fact that this omega is a continuous variable, right? So we have to compute this Fourier transform for all possible values of omega, right? Omega is periodic in 2 pi, but in a period of 2 pi you have to find for all possible values of omega. Second is the fact that the summation is running from 0 to infinity, right? So to find it exactly, I need to record it for infinite samples. This is especially problematic in our case because we are dealing with sinusoids, and if you want to get the right discrete time Fourier transform, the sinusoid has to be considered from 0 to infinity, right? So let's see how we'll solve them. So first problem is the fact that we have to evaluate this Fourier transform at all possible values of omega. Of course we can't do it. So what is the fix? I don't want to compute at all possible values of omega, so what do I do? Yeah, so this is, let us say, the axis of omega from 0 to 2 pi. Let's say the Fourier transform looks like this, but I can't find it for all possible values of omega. Huh? No, I cannot sweep omega from 0 to 2 pi in a continuous fashion. So what can I do? I take a discrete frequency points. So let us say I take n frequency points. Okay. Like any sane person will do, I'll take uniformly spaced frequency points. So this range of 0 to 2 pi I have divided into n points. So I'll basically take the spectrum at these frequency points. Okay. So omega, instead of computing for all omega, at what frequency points I am computing? 2 pi is the range. I have divided into n points. So I am stepping in what increments? 2 pi by n. So I am doing at k times 2 pi by n, where k takes the values from 0 to n minus 1, because n is same as 2 pi, right? Okay. So this will basically solve this guy. And of course, here what is the solution? Simple solution. I can't record the signal for infinite samples. What is the practical thing to do? You basically take it for finite record length. That's all. Okay. So let's see what happens when we do that. So the original Fourier transform of this, the summation went from 0 to infinity, x of n e power minus j omega n. Now what I am going to do is I am going to take omega only at these frequency points where k is going from 0 to n minus 1, and I am going to make sure that I am recording the signal x of n for a finite number of samples, and I will call that as NR, which I call as record length. Okay. So what will happen? So instead of finding at all omega, I am computing at these points. So this is no longer a function of omega. It is a function of what variable? K. So I have x of k to be equal to summation. What is the upper limit of the summation? It's NR minus 1. So I have a total of NR samples. Okay. X of n e power minus j. I don't have omega. Instead I have k 2 pi by n. Done. So if in the inverse transform, I was having something like this. X of n was 1 by 2 pi. So integral 0 to 2 pi. This was the original inverse calculation. So here what will happen? I'll have 1 by 2 pi. So what will happen to the integration? Summation. What will the variable that will be summed? I mean earlier it was omega. Omega was integrated. Now what will be summed? K. K will span from 0 to, it's written here, so n minus 1, and this is x of k. And what is d omega? Sorry, what is d omega? I mean earlier d omega was a small increment in continuous time, I mean continuous frequency. Now what is the step at which I can increment my frequency? So d omega is essentially 2 pi by n. So this simplifies to, maybe I'll put it up. So this simplifies to 1 by n. Sorry, I made a mistake, right? Here I have e power j, right? I missed it. Apologies. So here I have e power j omega and d omega, right? So here I'll have e power j 2 pi, same thing. Okay. Fine. So this is the modified version, and again here as of now there seems to be no relation between this number of frequency points n and the record length nr. Looks like we can choose them arbitrarily, but before jumping into any conclusion, let's look at something. So here let us say I calculate x of n plus capital N, and remember capital N is the number of frequency points I am taking. What is that? It's 1 by n summation over k. So I am going to replace small n by capital N plus small n. So what does it simplify to? It is same as x of n. Okay. So what this means, I can take, let's say I take a sequence x of n, record for nr samples, find its Fourier transform like this by computing at discrete frequency points, and then I try to reconstruct the signal back. It looks like the signal is periodic with n samples. I mean this shouldn't be surprising because see, when we looked at sampling in time domain we sampled. So when we sampled in time domain, what happened to the frequency spectrum? We had a periodic repetitions in frequency domain, right? So when you sample in one domain, In the other domain, you expect the periodicity. So now what essentially we are doing is we are sampling in the frequency domain, right? Because we are basically taking samples of a discrete time Fourier transform at these frequency points k 2 pi by n. So now what's happening is sampling is happening in frequency domain. So you do expect some periodicity in time domain. That's what is happening. Okay. So what happens if let's say I take some discrete time sequence. I mean, this is a discrete time sequence. I am drawing it as a continuous time signal for simplicity. Okay, so let us say this is total of NR samples. I take the Fourier transform by taking n points, and then I reconstruct the sequence back. I'll have a periodic repetition of this guy, starting from n to 1 and so on. Again, this all discrete time signals. I am drawing it like a continuous thing for simplicity. So this, let's say NR minus 1. Fine. And here you can see that I assumed inherently that n is much greater than nr, right? What will happen if I choose n to be less than nr? Yeah, basically we'll have the same thing we saw in aliasing. So this is nr. I'll have periodic repetition starting from n, so that will be somewhere here. So what will happen is the initial and the last few samples, they will get corrupted in this process. Again, this is similar to the aliasing we saw in sampling. Okay. And I mean, again, show that I can take an example. So here I have considered a discrete time sequence going from 0 to 11. So I have a total of 12 samples. So what I did, I take a 10-point Fourier transform. Basically, I capture the Fourier transform at only 10 discrete frequency points, and I try to reconstruct the signal back. Again, as you expect, since we have extra 2 here, the initial 2 and the last 2 samples will get corrupted. And that's exactly what you get here. You see that the blue ones are the reconstructed sequence, and the yellow ones are the original signal. The first 2 and the last 2 are corrupted. Okay. So what is the conclusion? How should I choose n and nr? N should be greater than nr. I mean, greater than or equal to nr. And if you assume n to be greater than nr, it inherently assumes that, I mean, we'll have something like this. Again, all discrete time sequence. This is n. The remaining samples are inherently assumed to be 0, right? So instead, what you can do is, instead of filling them with zeros, you can ask them fill with your required signal, right? Instead of recording for a shorter number of points and computing more number of points in the frequency spectrum, I can as well make n to be equal to nr. That way, I'll also make use of these samples for computing the spectrum. But here, these are basically assumed to be 0 inherently. Other way to think about this, see, now we will be dealing with sinusoidal signals, and what we will most probably do is capture the sinusoid for one period. Again, these are all discrete time sequence. And when we compute the spectrum, we want the signal to be assumed to be a periodic signal, right? So ideally we want this guy to be repeated like this. But if we choose n to be greater than nr, what we'll have is a sinusoid and then some zeros, and then you'll have something like this. So this is not a great thing to do. So the usual choice is to keep the record length and the number of frequency points to be same. Okay. And when we do that, the equation changes. So let me just write the equation alone. So the only change is the record length here is same as the number of frequency points, at which we are computing the spectrum. Okay, and this is called the discrete Fourier transform. Or DFT. Right, the other one x of e power j omega is basically the discrete time Fourier transform, where the sequence we are dealing with discrete time, but the sequence we are dealing with is discrete time, but the frequency variable is continuous, but here everything is discrete. Okay, great. And yeah, and remember, so here we are taking interval of 2 pi, splitting into n equal frequency points, something like this, and each of these points are called frequency bins. Okay. So earlier we had frequency omega, so now we have the variable to be k, and k will go from 0 to n minus 1. Okay. So 0, 1, 2, 3. And this is an increment of 2 pi by n, remember, if you convert to frequency. So if I take, let us say, bin L, what is the corresponding frequency value? 2 pi by n, that is the increment into the bin number L. Fine. So this is 2 pi by n. Second is 2 times 2 pi by n, this is 3 times 2 pi by n, and so on, that's all. Okay, great. So the bottom line is that the discrete time Fourier transform had issues. So let me quickly write that. Two issues are the fact that the frequency variable omega is continuous and the limit has to be infinite. We sort of overcome it by doing two things. We record the signal x of n for a finite number of samples, and in this case for n samples, and then we also compute the spectrum at n frequency points. So we can think of it like this. I can consider this discrete Fourier transform as taking x of n for n samples, computing the discrete time Fourier transform, and then taking samples of the discrete time Fourier transform at k times 2 pi by n. That's other way to look at it. Okay, and this fact of considering the signal x, this act of considering the signal x of n for only n samples can be thought of as multiplying x of n with a sequence which is 1 for n samples, right? Is that clear? So this guy is often called the rectangular window. I'll just say it's rect n of n. This signifies that it has n ones. Okay. So what DFT is basically? It's basically computing the discrete time Fourier transform of this sequence and then taking the samples at k 2 pi by n, where k varies from 0 to n minus 1. So, okay. And usually, you can choose this number of n. If you choose it to be a power of 2, it turns out you have fast algorithms to compute the process. But of course, in 30-40 years back, this made sense. But now with the level of computation we have, this doesn't make sense at all. You can choose n to be anything. But of course, for legacy reasons, we still choose n to be a power of 2. But otherwise, there is no other reason to do. Okay. So let's finish the discussion. So remember, we started with finding the power spectral density of our ADC output. There? Okay, yeah. 1 by n factor is there. No, there is no 1 by n factor in frequency, right? Inverse you'll have. But even in the original DTFT inverse, you had 1 by 2 pi. Okay? So we started off with this, right? We were trying to find the path spectral density of our ADC output, and we initially computed it as magnitude squared of the discrete time Fourier transform, expected value of it scaled by n. Okay. And now we will no longer compute this discrete time Fourier transform. We will take the discrete Fourier transform. So we will compute the path spectral density as expected value of mod x of k square, that's all. Instead of taking for all values of omega, I am taking for discrete values of omega, right? And here if I were to find the total power, I basically did 1 by 2 pi integrated over, the appropriate frequency range. So here how will I find the power? Yeah, I mean we'll have 1 by 2 pi, integration becomes summation over k. This is basically okay, SVP of k. Sorry, this is, I made a mistake. So this all k, right? There is no, and this must be v not x. Apologies. So this all v, right? Okay. Yeah. So let's finish this. So this we are trying to rewrite here. So this becomes SVV of k, and what is d omega? Here we can increment in steps of only 2 pi by n. Okay, so this sort of cancels, so we'll have 1 by n summation over k. So this how we'll compute the spectrum in practice and measure the signal to noise ratio, right? So
this is what we want, but we are doing using this way to that.
Left is what ideally you want, but that is not practical to find, and that's exactly why discrete Fourier transform evolved, right? Else DTFT is very good. The problem is we can't compute it. So here when we have to plot this guy using discrete time Fourier transform in a one-sided PSD, I had sinusoid and noise like this. So this is omega. So now when I compute it in discrete Fourier transform, what is the x-axis? What is the variable here? K. And here it varied from 0 to pi omega. So what will be the range k will take? Remember that range of 0 to 2 pi was split as 0 to n. So now pi is what? N by 2. So basically now I'll have only discrete points like this starting from 0 to n by 2. Okay, and how will this sinusoid appear here? It will be an impulse, at least for now it should appear like an impulse like this. And what about the quantization noise? That will look like a bunch of impulses, white noise. To find the signal power, again I will take this guy, strength of this guy. This will give me the signal power. To find the noise power, what do I do? I mean, here there are like total of, let us say, n by 2 bins, right? N by 2 points. Signal is occupying this bin. All the other bins are occupied by noise. So to find the noise power, what can I do? No, I mean to find the power from the path spectral density, what is usually done? We have to add the path spectral density, but here we have to add the path spectral density, but one bin is already occupied by signal, right? So to find only the noise power, what should be done? Yeah, I mean, yeah, you can either take the entire power of the signal by summing up this and subtract the signal, or the other thing is I can only, I mean that's equivalent to saying that I'll sum up only these bins, right? If I take the sum of the entire PSD, I get the total signal and noise power. I'll have to subtract the signal power, which is basically this guy alone. So instead I'll sum up the content of all the bins except the bin on which the signal is lying, and that gives the noise power. So then you take the ratio, you get the signal to noise ratio. Okay. So this is what we expect the spectrum will look like, but in the next class we will see what all can go wrong here. Let's stop here.